Hello. In this video, we're going to take a look at an IC DAC, and I have selected the DAC08, which is an 8-bit high-speed DAC. And if you take a look at the datasheet, you will see that it is a DAC that can be configured for both unipolar and bipolar output. So I've taken some sample configurations out of the datasheet to illustrate both the unipolar and bipolar output configurations. We're going to start with the unipolar configuration, where the output voltage goes from 0 towards the full scale range, whereas in the bipolar configuration it will go from minus to plus the full scale range, approximately. So notice that I have my DAC in the middle. I have my digital input, because it is an 8-bit DAC. The digital input is comprised of 8 bits, B1 through B8, where B1 is the MSB, most significant bit, B8 will be the LSB, or least significant bit. Then I have for my inputs, 2 reference inputs, what's labeled in the datasheet as VREF plus and VREF minus. In this particular configuration, VREF minus is being tied to ground, and the positive reference voltage is being applied externally as 10 volts. And then it has 2 complementary output currents out of pins 4 and 2, which are labeled in the datasheet I-out and I-out bar. And since it is a current DAC, since it provides an output current, in order to get an output voltage in this particular configuration, the output current I-out is being fed into a transconductance amplifier to convert it into a voltage with a feedback resistor of 5 kilo ohms, in order to get an output voltage, which as given by the datasheet is equal to V-out equal to I-out times RF. My output current in this case is being determined by the reference current. My reference current is the current into that reference voltage pin, and it can be calculated as Iref equal to Vref divided by Rref, which we've selected as 5 kilo ohms. So this will be 10 volts divided by 5 kilo ohms, or 2 milliamps. And that's going to be the range of my output current. I-out is going to go from 0 to 2 milliamps. My output voltage is going to go in the unipolar configuration, as we shall see, from 0 to the full scale range minus 1 LSB, where the size of the LSB is going to be the full scale voltage, VFS, divided by 2 to the n, or in this case, the reference voltage applied is 10 volts, so 10 volts divided by 2 to the 8, which is the number of bits, which is equal to approximately 40 millivolts. So that's the size of my LSB. If I were to divide my current, overall current of 2 milliamps by 2 to the 8, then I will get my LSB step for the current, which is 8 microamps. And so I-out changes, increases as 8 microamps per bit. My output voltage increases by 40 millivolts per bit. And then my maximum output voltage I will calculate as my full scale voltage of 10 volts minus 1 LSB, or 10 volts minus 40 millivolts, which is 9.96 volts. And if you look at the table provided in the datasheet, you will see that that's more or less what we're getting. I've added there 4 possible values for the digital input: a value of 0, where all my bits are set to 0. That will be the first line here. You'll notice I expect both my output current and my output voltage to be equal to 0, and that's what I get in the table, which is again just taken out of the datasheet for the device. For an input, digital input equal to 1 LSB, meaning just switching from 0 to a digital 1, meaning switching the last bit, bit 8, to a 1, I get 1 LSB step both in the current, 8 microamps, and in the voltage, 40 millivolts. Then at half scale, which basically corresponds to the point where the most significant bit is set to 1 and all the others are set to 0, I get half the full scale range. So for the current, I will get 1 milliamp, which is half of the 2 milliamps full scale current range. And for my output voltage, I get 5 volts, which is half of the 10 volts full scale. And then finally, for my full scale, that is when all my bits are set to 1, I get 2 milliamps for my current, and then I can convert that to a voltage by multiplying it times the 5K resistor. Notice my output voltage is 1 LSB below that full scale voltage range. 1 LSB or 40 millivolts below the 10 volts, as we have previously seen. Next, we're going to take a look at the DAC08 in a bipolar configuration. Notice that this almost identical connections as before. I still have my digital input being applied, my Vref minus being tied to ground, my positive Vref set to 10 volts. And in this case, my output is being connected to a transconductance amplifier, but notice that it is a differential current to voltage converter, meaning I'm applying both inputs, the I out and the I out bar inputs as the input of my transconductance amplifier. And again, according to the datasheet, I am connecting the feedback resistor to equal to 5K and an identical resistor to ground from the other op-amp terminal. And according to the datasheet, my output voltage is now equal to RF times I out minus I out bar. Now, since I out and I out bar are complementary currents, it just turns out that when my I out is set to 2 milliamps, my I out bar is going to be set to 0 milliamps, and the opposite is true. When I out is set to 0 milliamps, my I out bar is going to be set to 2 milliamps. So the sum of the two is going to be equal to the overall 2 milliamps that comes from, we already said the Iref, the full scale current, is equal to Vref divided by Ref, or 10 volts divided by 5 kilo ohms, which is 2 milliamps. And again, I out and I out bar go increasing or decreasing such that the sum of the two is equal to 2 milliamps. And in that case, the output of my op-amp, like we said, is I out minus I out bar times RF. So in this case, we expect that the output is going to vary, not from 0 to the full scale voltage range, but rather from negative full scale voltage range, which corresponds to the point when I out bar is equal to 2 milliamps, to positive full scale voltage range, which corresponds when I out is equal to 2 milliamps. So my output voltage now ranges from roughly from negative 10 volts to plus 10 volts. We're going to see that in the table below. And if we take a look at the table, I've represented again 4 possible values for my digital input. One is for my negative full scale range, which corresponds to when all my inputs are set to 0, all my bits. Notice that under those conditions, my I out is equal to 0, just as in the unipolar case. My I out bar is 2 milliamps, roughly 2 milliamps, is slightly higher than that, specifically 40 microamps higher. And then my output voltage is roughly negative full scale range. Notice that there is a little offset there. For my negative 0, which corresponds to the point where my most significant bit is set to 0 and all the other bits are set to 1, I get my current roughly divided equally between I out and I out bar. I out is 1.016 milliamps, I out bar is 1.024 milliamps. Notice that there is an 8 microamp step between the two. 8 microamps being the size of the LSB for current. And my output voltage is sitting at a negative 40 millivolts or negative 1 LSB for the output voltage. For my positive 0, which is when my most significant bit is set to 1, all the others are set to 0, the values for IOUT and IOUT bar are swapped now. IOUT has increased by 8 microamps. IOUT bar has decreased by 8 microamps. My output voltage is positive 40 millivolts. And again, notice that because I have now the effect of both output currents, the actual size for my voltage LSB is double what I had in the unipolar case. And then finally, my positive full scale, which is when all the bits are set to 1, I get 2 milliamps for IOUT, 0 for IBAR, and positive full scale output voltage for the out, which is plus 10.2 volts in this case. Now that's one of the applications that is specified in the DAC08 datasheet, and the flexibility of being able to configure it for both unipolar or bipolar outputs. There are other performance characteristics that we can look at in the DAC08 datasheet or most other DAC IC datasheets. And I wanted to go over some of them just so that we get an idea for what are the particular specifications for a DAC. Typically, one of the specifications will be the resolution of the DAC, which is specified either as the number of bits or the number of digital states, which is 2 to the n, n being the number of bits. Most often it's going to be as the number of bits, so they will talk about an 8-bit DAC or a 12-bit DAC or a 16-bit DAC. The accuracy is different from the resolution. The accuracy basically indicates how close the real or practical output of the DAC is to the nominal output. And so the accuracy specification will typically be given as the maximum deviation between the nominal output and the real output out of the DAC. And it's typically going to be measured in LSB, so you will see an accuracy specification of 1 LSB or half an LSB, or sometimes specified as a percentage of the full-scale range. There are typically 4 components that play a role in the accuracy. One is the offset error, which corresponds to the output voltage V out when the digital input is equal to 0. We will expect ideally that the output will be 0, the analog output out of the DAC when the input is 0, but in reality it's going to be something that's different from 0. Now the offset error is typically a constant, and so it can be calibrated out, and so when one is using the DAC, it can take a first step of measuring the output when the voltage input or when the digital input is set to 0, and then subtracting that from the output of the DAC. There is a gain error, which is basically the difference between the maximum value, the nominal maximum output voltage out of the DAC, and the actual maximum output voltage when all the bits are set to 1. Then there are the linearity errors. The differential nonlinearity is basically the maximum difference between the actual step size and the ideal value of the LSB, the least significant bit. So ideally, every single step in input word, every single bit increase, should correspond to a 1 LSB increase in the output voltage. In reality, there's going to be some deviation from that, and the maximum deviation between the increasing output voltage corresponding to one digital step and the LSB, that's going to give you your differential nonlinearity. And the integral nonlinearity, or INL, is the deviation or the maximum deviation from the DAC transfer function and an ideal straight line. We're going to take a closer look at these 4 parameters in a minute. Before we do, though, I wanted to go over some of the other parameters that you will encounter in a DAC datasheet. Sometimes they will refer to the monotonicity, and to refer to a DAC as being monotonic, it simply refers to the fact that the analog output voltage always moves in the direction of the digital input. So if the digital input increases, the analog output increases. If the digital input decreases, the analog output decreases. You can see that if you have large errors, let's say large errors in differential nonlinearity, you could run into situations where a DAC will not be always monotonic, which will cause data losses and basically an error in the output. And so it is important for a DAC or an ADC. It's important, the idea that they be monotonic, that the output goes increasing for increases in the input, and the output always decreases for decreases in the input. Other things maybe, related to the reference, whether it has a reference voltage or a reference current, what is the range of the reference voltage and reference current, the speed, an important one for DAC performance. One of the parameters that is going to define the speed of a DAC is the settling time, which measures the time from when a change is applied at the input of the DAC, a change in the digital input, to when the output voltage is settled within some tolerance of the final voltage, typically expressed as LSB. So when it is settled to plus minus 1/2 of an LSB, for example. The temperature coefficient, which refers to the changes in the output of the DAC for variations in temperature. Typically, it's going to be expressed as ppm, or part per million, for degrees C. And then other things that will come specified will be the digital input format and whether it is a serial format or parallel. If it is serial, what type of serial interface, whether it is SPI or I2C or whatnot. Logic input levels, because you have a digital input, typically will come specified what is the maximum voltage that the DAC will interpret as a logic low, or the minimum voltage that it will interpret as a logic high, or VIH, VIL. Output range, what is the dynamic range, the compliance, if you're talking about the current output, etc. And then other things will just be different types of packaging, whether you have a single DAC in a package or a multiple DACs in a package, and so forth. And I mentioned that I wanted to get a little bit more into detail with the different sources of accuracy errors, offset error, gain error, DNL, and INL. And so I've represented a few plots here to try to illustrate what those mean. So we've already mentioned that the offset error is equal to the output voltage when the digital input is equal to 0. Ideally, we would want the output voltage to be equal to 0 when the digital input is 0. But we said that it's not going to be equal to 0, and so if the green dots represent here my nominal output values for my different possibilities for digital input, my digital input states, and I were to represent my actual output with orange dots, let's say, if I had an offset error, let's imagine my output, instead of being 0 when my digital input is equal to 0, it might be something different from 0, like in this case, half an LSB, for example. And then it might sit right on top. On another location, it may go to 1 LSB, maybe something less than that, go back to 0, slightly negative. Let's imagine my output was something like that. I notice that in some cases I have deviations from my straight line. If I were to measure my offset voltage, this is what will represent my offset voltage. The difference between my analog outputs for my digital input having a value of 0 and the actual 0. This will be my offset error. Next, the gain error. We've expressed it as the difference between the maximum output voltage and the nominal maximum output voltage. So again, let's imagine that my green dots here represent my ideal set of output values for the different digital input states. And now let's imagine that my actual output was something that started deviating at different points. And then it ended up something like that. Well, if I look at my maximum nominal output voltage and my actual maximum output voltage, this will be my gain error, the difference between the two. So in this case, it's about 1 LSB. In the case of my offset error before, this was about half an LSB. The LSB being each one of those grid lines represents one LSB. Now, in terms of the differential nonlinearity, the DNL, notice I have said there is the difference between the changing output voltage, delta V out, for an increase in digital input code. So you go from a digital input of X, state X, to X plus 1. The difference between the changing output voltage and one LSB. And so, again, I expect that for every change in input code, I will get an output increase of exactly one LSB. That's what the ideal set of data points represented in green there represents. Let's imagine that I have something different. I start okay, but then I'm slightly different from it, and then I sort of go back, and then at some point it increases by a lot. Slowly comes down back to normal. So notice that my maximum step size in this case, it's between these 2 points. It's kind of a very large. Let's make it a little bit less. Let's make it a little bit more realistic. Let's imagine it's something like this. Basically, from this point to that point, I have a difference of this will be one step in digital input, and it will correspond to a 1 LSB step in digital output, but instead it's a 1 LSB and a half. And so my delta V out is equal to 1.5 LSB. Therefore, my differential nonlinearity is half an LSB. So it's the delta between that maximum difference and 1 LSB. And then finally, the integral nonlinearity represents the maximum deviation from straight line. So imagine in the case where I had something that goes like this, then it slowly returns back to normal. The green here represents my straight line, and the maximum delta will be at this point. And it will be a maximum delta of 1 LSB, so that will be my INL, or integral nonlinearity. It will be that maximum deviation from the straight line.